Okay, let's continue with the next presentation. Let's see the other side of the coin instead. With Yuting,
Yes.
we present this analysis and inversion of piezometric levels. Thank you.
Yes, good afternoon, everyone. My name is Yueting Li, and today I'm going to show you my PhD project, Bayesian inversion of piezometric and displacement data to characterize the aquifer properties. As we all know, the numerical simulation has been widely used in land subsidence modeling, and commonly these numerical outcomes are affected by the uncertainty of aquifer properties, such as hydraulic conductivity and compressibility. So this work, we aim to develop a surrogate-based Bayesian inversion to quantify these uncertainties of these parameters, whereby we can get a better understanding of process and improve the groundwater management. It was noted here this work is part of reservoir project. So if you are interested, you can check our homepage. The proposed framework involves Markov chain Monte Carlo method. Is a common method to estimate the posterior distribution. Normally, MCMC calls for lots of realization of numeric forward model. But unfortunately, our simulators are too expensive to run many times, so we exchange them with surrogate models. Additionally, we take advantage of INSA technique, which is well known for the long-term deformation measurements over a larger scale. So we applied this framework in Alto Guadalentín, which is located in the southeast of Spain. So here is a typical water scarce region. The groundwater production has been initiated since 1962. And by 2012, the piezometric level has dropped down 150 meters. As a result, this region undergoes one of greatest subsidence rate in Europe, which is over 10 centimeters per year. Yes. Like, according to the geologic survey and the deformation analysis, the substance of rate actually is highly related to the thickness of clay. And we also know the underlying sand layer is the main productive layer. So we only focus on the calibration of compressibility of clay and conductivity of sand. And for this aim, we also build a 3D static model to characterize the geologic structure. I didn't show here, but the element size has been refined to the tens of meters to guarantee the precision of the numeric model. Regarding the numerical methods, we employed 3D coupled groundwater flow and geomechanic model. And this variable saturated flow model is designed for the large drop of water table. And for the simplicity, we split the simulation by the availability of sub images. So in the first time window, the groundwater flow model is activated alone to compute the pore pressure and calibrate the conductivity with the piezometric records. Then we run the couple model for the whole 50 years. Similarly, the compressibility of clay can be calibrated with SAR data too. So all the boundary conditions are provided by the Spanish group, but we didn't include the rainfall or the irrigation recharge. From our perspective, these recharge flows are too hard to infiltrate in the saturated zone because they have the water table has dropped 150 meters. So within our groundwater flow model, the only variable is the conductivity of sand. Other parameters are deterministic, so the drawdown can be represented as the function of conductivity. Here we use the drawdown as the output rather than the pressure head because drawdown is less affected by the initial head. Then according to the Bayesian theory, the likelihood function of conductivity depends on the misfit between the forward model and measurements. And as I said, our simulators is time consuming. So we resort to the surrogate model, specifically the polynomial interpolations. And now I'm going to show you how we construct the surrogate models to compute the drawdown for these 9 monitor wells. In Lagrange form, the new outputs can be defined as the linear combination of numerical results over this given interpolation points. So how to choose these points is essential for the approximation, but I will skip this part because of time. If you want to know more about this, you can check these Leja points. And here are the response surface obtained by surrogate model. From these plots, you can have an idea how the drawdown propagates with different conductivity and time, but I won't go into details. Basically, this response are reasonable given the physical location of these pumping wells and monitor wells. It's also important to access the performance of surrogate models as the proxy of numeric simulators. What I want to say here is the accuracy of our surrogate models is good enough to be the forward model. And in this way, we can conduct MC sampling 10,000 times in minutes. And these samples review the log K, follow this normal distribution. So K can be represented by this log normal PDF. And this median is the most likely value for the conductivity given the available piezometric records. And now we're checking how the performance of this calibrated results. So according to the groundwater flow model, the drawdown mainly occurs within the sand layer and reach 120 meters in the first time window. These patterns here also accord with the distribution of pumping wells. Quantitatively, the numerical results are pretty much in agreement with the piezometric records. So far, we're quite satisfied with this calibrated results. And now we can move on to the couple model. So first, the boundary conditions has been extended for the second time window. And as planned, we should calibrate our compressibility of clay with the same strategy. However, we have met the problem of prior distribution, specifically the upper boundary, because a larger compressibility leads to a greater compaction and small porosity, which make our couple model harder to converge. Despite this, we can still have a look at this preliminary calibration results. So let's also begin with the drawdown field. On the basis of first time window, the drawdown keep increasing and propagating. Besides, we have another 5 monitor wells available for the second time window, but 5 wells are too few to get the whole picture. That's why we attempt to use the SAR images. And now we're looking at the vertical substance field. The first plot is the cumulative substance of the whole simulation. And you can see there are 2 substance centers, which are formed separately in 2 different time windows. And if we focus on the second time window, both SAR images and our couple model demonstrate the the substance is basically proportional to the thickness of the clay. So they're pretty much matched in terms of the patterns and amounts. For the quantitative analysis, we also choose like 70 pixels from SAR images. So the substance rates of this point are characterized by 3 different INSAT data sets, which work in different time series too. So we compare them to the corresponding numerical results respectively. And although there are some underestimation over the age of clay, but the numerical model pretty close to the SAR measurements in the first 2 plots. But after 2010, the SAR images indicates a deceleration of substance, which is not captured by our couple model. But in general, this result seems satisfactory. And next, we're gonna introduce the hysteresis, and we will continue our Bayesian inversion for the calibration of compressibility. So in conclusion, the employed numeric model are able to describe both piezometric and deformation fields in response to the groundwater extraction. And the surrogate model, based on the polynomial interpolation, provides a good approximation of our groundwater flow model and significantly reduce the computation costs. At last, the present inversion method has successfully quantified the conductivity, the uncertainty of hydraulic conductivity of sand. The calibration of compressibility is still ongoing. So that's all for my presentation. Thank you.
Thank you very much. There's time for questions.
Thank you. Really interesting presentation. In the end, when you were comparing the time series of subsidence observed versus modeled, it looked like it was pretty elastic.
Yes.
Like I wasn't seeing a lot of long term. But you mentioned that you were going to work in hysteresis. So you're going to work in like an inelastic component. And I was just curious, like if you saw the elastic behavior everywhere, or if there were some areas where it was more
No. So far as everything is elastic. So the next step we're gonna introduce like hypoplastic. But actually it's not the axis here is the point indices, so it's not really the rebound of this point. Yeah, it's my fault because yes. Yeah, it's confusing. Yeah, X actually is this 70 points indices. So actually this just showed it's not really the time series plot. So that's why it's confusing that you're missing it. They have elastic behavior. Yes. Luckily because our pressure head seems always going, they never go up. So
More questions?
Thank you for the presentation. I was just wondering if you have verified the K and Cm against some data or some measurements.
yes, actually for the, okay, I will go here. So for the hydraulic conductivity, we have some 9 monitor wells with 20 years piezometric records. And for the couple model, for the compressibility, we're mainly use the INSAR data. Yes.
Okay.
One more question maybe?
Do you have the opportunity to compare your conductivity data with pumping test results, or?
No, it didn't conduct any test.
Okay, if there are no more questions, let's thank the speaker again.